Hello again, and today we're looking at nuclear physics, radioactivity, and the different types of radiation that can be given off by different materials. I've got a Geiger counter here connected to a counter, and it's measuring the radiation in the room. It's a little bit higher than normal at the moment because I've got some radioactive sources. Typically what you'd find if you measured the radiation without sources in the room, you'd get about 10-12 counts per minute, and at the moment we're getting significantly more than that. Now, background radiation comes from various different places. Some of it comes to us through the atmosphere as cosmic rays, some of it comes to us in the food that we eat, depending on what soil it's been grown in or the things that we drink. If we go to the hospital and have an X-ray or a PET scan, something like that, or if we work with radioactive materials in a hospital or a nuclear power station. But the most common source of background radiation is actually from rocks and the radon that's sometimes released by those rocks. So, for example, I have some rock samples here. They're in glass so that they don't get broken. They've got quite a high radioactive count, so the counter goes up significantly faster, and they tend to be igneous rocks, volcanic rocks, often containing small amounts of uranium. But you're perfectly safe with these, and even in parts of the country like Edinburgh or Cornwall, Cornwall particularly where they have the old tin mines, they have a possibility of a build-up of radon gas. They simply need to add a membrane to the bottom of the house to stop the gas building up, or have pumps like a ventilation system to make sure that it doesn't build up. So there's a fair amount of radiation that we're exposed to daily, and it's well within safe limits. But if we come back to the particular types of radiation we'll be studying at GCSE, there are three types which we look at. There is alpha radiation. Now, alpha radiation is a helium nucleus. There's some notes that follow. It has a mass of 4 atomic units because it's made of 2 protons and 2 neutrons, and it has a charge of +2. It's the big hitter in terms of radioactive emission. So you will find that it is the most ionizing, it's most capable of knocking electrons out of an atom, making it ionized, which can of course cause damage if that radiation is ionizing the atoms in your cells. It can cause the cells to die, or it can cause them to mutate. I have an alpha source here. And it is americium, which is the radioactive source that is used in smoke alarms. So we keep it in a wooden box with its label on, and it has a lead cover. Which, if I remove, reveals the source, and the radioactive source is held by tongs rather than by the hands, and it's generally pointed away from you. And my Geiger counter isn't picking up the radioactive source at the moment because it's pointed away from the Geiger counter. But even if I turn it to point towards the Geiger counter, we won't get much of an effect until we are really quite close. There we are. Now we're picking up the radiation, and that's because alpha radiation, being so massive with 4 atomic units and also having that +2 charge, tends to interact with atoms very quickly. So even the atoms in the air, you have to be very close. And indeed, a piece of paper will cut the count down significantly. Make the paper a bit thicker, and the count very quickly drops And if we take something like aluminium, the count drops very quickly. There's still a bit of radiation getting through, and the reason why the bit of radiation is getting through is because Americium also gives off a small amount of gamma rays. Now gamma rays, they're the high energy electromagnetic waves that you've studied, and they have no mass, they have no charge, they are very weakly interacting and very weakly ionizing. Got here a pure gamma source, which is cobalt, again stored with a lead cover, and again, now here's my gamma rays, and my piece of aluminium makes very little difference at all. In fact, even a big chunk of aluminium makes very little difference at all. So that's why we were still getting a signal from the Americium, not the alphas, but those gamma rays that it gives off as well. Now, all we can do to stop our gamma rays is with a piece of lead, and it needs to be quite a thick piece of lead before it really starts to make much of a difference. Okay, so there's still a fair amount of gamma radiation getting through. However, gamma radiation spreads out in all directions, the same as light. So as I bring my source away, the count rate is dropping. The closer you are, the higher the count, because more of the radiation is hitting the Geiger counter. As you move away, it's reducing because it's further away. Gamma radiation can travel a very long way, and it can travel through most things, and indeed that's what happens most of the time. If we're exposed to gamma radiation, it just goes straight through us. It's only when we're exposed to a lot of it that it can become dangerous. So that's two of the types of radiation. There is a third, and that is beta radiation, and beta is our electron. If I reset the clock for the beta, so we're dealing here with a fast moving electron from the nucleus, and I've got a strontium source here. Now, people often say that beta radiation is the middle. Okay, got a very high count rate at the moment, and again you see the closer I am, the more sensitive, the further away, the less, and that's because it's spreading out. Again, it's spreading out in all directions. Now if I take a piece of lead, you can see how much of a difference it makes. Okay, so beta radiation is capable of going through air, it can go through paper, it's stopped by lead. But what's interesting and what's useful with beta radiation is that some of it will be stopped with aluminium. And the more aluminium you have, the lower the count becomes. So if you're trying to measure the thickness of your piece of aluminium, 1, 2, 3, or a thicker piece, and we can make use of that property of beta radiation. Now, because beta radiation is charged, it has the charge of an electron, -1, and alpha radiation is charged, it has the charge of +2 because there's 2 protons in there. Those radiations will be affected by an electric field. The alpha will move towards the negative side, the beta towards the positive. They'll also be affected by a magnetic field. Gamma radiation, on the other hand, will go straight through because it has no charge. This is the first of 3 short video clips about radiation. This one particularly, the types of radiation. I'm only talking about ionising radiation here, and I'm only talking about the kinds that show up at GCSE Science. So, we have 3 types of radiation to consider, and they are alpha, beta and gamma. And each one has a symbol taken from the Greek alphabet. Alpha looks like this, beta like this, and gamma and alpha on its side effectively. You might recognise the gamma symbol as the one from the cancer charities, as of course gamma radiation can be the cause of, but also the treatment of various types of cancer. If we then consider the mass of these 3, alpha is made of 2 protons and 2 neutrons. It's basically a helium nucleus, and that means it has an atomic mass of 4. Beta is an electron, but it's an electron from the nucleus, and that means it's got a very low mass. It's 1 over 1800 times the atomic mass. And gamma is part of the electromagnetic radiation, and therefore it has no mass at all. The next thing to consider is the charge of these objects, because that will affect how they move in an electric field and magnetic field. Alpha, because of its 2 protons, has a charge of +2. The electron has a charge of -1, so does beta. And gamma, being an electromagnetic radiation, has a charge of 0. Which means that whichever way an alpha particle moves in an electric or a magnetic field, the beta particle will move in the opposite direction. As for the gamma, it will go straight through as if the electric field or the magnetic field isn't there, because it has no charge at all. Now, I can't tell you which of these 3 types of radiation is the most dangerous, because it depends on the circumstances, but there are a couple of things that we can consider. The first is how ionising they are. Now, ionising means stripping electrons off or adding electrons to atoms, and of course, if that's happening to the atoms in your DNA, in your cells, it can be very dangerous indeed. Alpha has a high ionisation rate. Beta, we often talk about a middle or medium, and gamma has a low ionisation rate. So you might be thinking, okay, alpha is the most dangerous, then beta, then gamma. But that's not always the case, because we also need to consider how far they travel. Now, alpha is stopped by a sheet of paper. Or by a few centimetres of air. Let's say 5 centimetres of air. So your skin is more than enough protection unless it's a very high alpha dose. Beta is stopped by 5 millimetres of aluminium, Al, or by about 2 metres of air. Gamma is stopped by perhaps 2 metres of lead, although some of it will still get through that, and it will travel forever in air. But what of course it will do is it will spread out through the air. So it will be less concentrated. And those are the properties of alpha, beta and gamma radiation.